At the lowest succinate concentration, malate cuts the rate in half. At high succinate, the loss disappears. The enzyme did not recover by magic, so what changed?
But this is malate. I remember malonate as the classic SDH inhibitor.
Good. Do not solve this from the name. Build the reaction first. Succinate dehydrogenase is the enzyme. Succinate is its substrate. Fumarate is the product.
So the table is measuring how one enzyme converts one substrate into one product, with malate added as the molecule being tested.
Exactly. Once the physical machine and the binding states are in place, the changes in Vmax and Km become consequences. Then we will return to every number in the table. Succinate dehydrogenase, abbreviated SDH, is a protein complex built from four subunits: SDHA, SDHB, SDHC, and SDHD. In the respiratory chain, the same complex is called mitochondrial complex 2. Its job in this reaction is to catalyze the oxidation of succinate.
So succinate is a small 4-carbon dicarboxylate that enters SDH as the substrate.
Fumarate is another 4-carbon dicarboxylate. It is the carbon product that leaves this reaction. Lock those positions in. Enzyme SDH, substrate succinate, product fumarate.
Oxidation means succinate must lose electrons. Who accepts them?
First, flavin adenine dinucleotide, or FAD. FAD is a redox cofactor attached inside SDHA. It temporarily accepts the electrons and hydrogen removed from succinate. Next come iron-sulfur clusters inside SDHB. These clusters are electron transfer cofactors. They do not turn succinate into fumarate. They carry the electrons through the complex. The final acceptor in the overall reaction is ubiquinone, also called coenzyme Q or coenzyme Q. Coenzyme Q is a lipid-soluble electron carrier in the inner mitochondrial membrane. After it accepts electrons and protons, it becomes ubiquinol, coenzyme QH2.
Then the overall reaction is succinate plus coenzyme Q becoming fumarate plus coenzyme Q H2.
One carbon reaction and one electron transfer path occur in the same protein complex. Now, place those four separate subunits. SDH is not one protein chain.
Which parts face the mitochondrial matrix?
SDHA and SDHB form the hydrophilic head on the matrix side. SDHA contains the covalently bound FAD and the catalytic region where succinate binds and is oxidized. SDHB contains 3 iron-sulfur clusters arranged along the electron transfer path.
And the SDHC and the SDHD.
They are hydrophobic membrane subunits. They anchor the complex in the inner mitochondrial membrane and help form the region that interacts with coenzyme Q.
Let me see if I can map them. SDHA handles the carbon substrate. SDHB passes electrons. And SDHC plus SDHD connect the complex to the membrane and coenzyme Q. Is that the division of labor?
That division of labor matters. The catalytic head can reach metabolites in the matrix. The membrane section can reach the lipid-soluble coenzyme Q pool. The location makes the dual function possible. Watch the chemistry at SDHA. Succinate loses 2 hydrogen atoms. A double bond forms between its middle carbons, producing fumarate. Because succinate loses electrons, succinate is oxidized.
FAD gains those electrons, so FAD is reduced.
The reduced FAD does not leave SDHA and float to another respiratory complex. It is a bound cofactor inside this machine. Its electrons pass to the iron-sulfur clusters in SDHB.
Then the clusters pass the electrons toward SDHC and SDHD, where coenzyme Q can accept them.
Coenzyme Q is reduced to coenzyme QH2 and remains mobile within the membrane. It can carry those electrons to complex 3.
So carbon and electrons separate. Fumarate continues in the TCA cycle, while the electrons enter the respiratory chain through coenzyme Q.
That is the useful model. Textbooks often list FADH2 as the product of this TCA step, which can make it sound like a diffusible carrier. That is shorthand. The reduced FAD stays bound inside complex 2, and its electrons move through the complex to coenzyme Q. It does not leave the enzyme the way NADH can move away from the reaction that produced it. The tricarboxylic acid cycle, or TCA cycle, processes carbon fuels in the mitochondrial matrix. The electron transport chain, or ETC, transfers electrons through inner membrane complexes and helps build the proton gradient used for ATP synthesis.
SDH touches both systems because its catalytic head faces the TCA metabolites, and its membrane subunits face coenzyme Q.
That is why SDH is also the only TCA cycle enzyme embedded in the inner mitochondrial membrane. Its TCA reaction and its complex 2 reaction are the same molecular event viewed from 2 pathways.
Does complex 2 pump protons when those electrons move?
No. Complex 2 transfers electrons to coenzyme Q, but it does not directly pump protons from the matrix to the intermembrane space. Complexes 1, 3, and 4 contribute directly to proton pumping.
Wait. If complex 2 does not pump protons, are its electrons useless for oxidative phosphorylation?
They are not. Electrons that enter coenzyme Q through complex 2 can continue through complex 3 and complex 4. Those downstream complexes still support the proton gradient. Complex 2 simply does not perform a proton pumping step of its own.
If SDH activity falls, succinate oxidation slows, and electron transfer from succinate to coenzyme Q also falls.
The carbon flux and the electron flow are 2 outputs of the same complex. Now bring in malate. Malate is a small 4-carbon dicarboxylate with a hydroxyl group. In this experiment, it is the added molecule whose effect on SDH is being tested.
It is not the enzyme, and it is not the normal substrate of the succinate to fumarate step.
Its pathway relationship is downstream. Fumarase is the enzyme in the next TCA cycle step. It converts fumarate into malate.
Malate and succinate are both 4-carbon dicarboxylates. Does that mean SDH might recognize both of them?
It makes overlapping recognition plausible. But resemblance gives us only a hypothesis. The rate data still have to classify what malate does in this experiment.
Now the name trap. Malate is not malonate.
Malonate is a 3-carbon dicarboxylate and the classic textbook competitive inhibitor of SDH. This question names malate. We must not import the malonate answer before reading the experiment.
Is real malate inhibition always a simple contest for the succinate site?
No. SDH can also oxidize malate to enol oxaloacetate, and that product can inhibit SDH strongly. Real malate-dependent regulation can be more complicated than one reversible binding step. The supply table can classify its observed kinetic behavior. It cannot prove that only one physical mechanism exists. We now need the kinetic model. Reaction velocity is usually compared using the initial velocity, measured before substrate is substantially depleted and before much product accumulates. 2 binding states matter from here on. Free enzyme, written E, means an SDH complex whose succinate binding region on SDHA is empty. The enzyme substrate complex, written ES, means succinate is bound there and is ready to be oxidized.
At low substrate, many enzyme molecules are waiting without substrate bound.
Adding substrate increases the chance that an available enzyme binds substrate, so the rate rises. At high substrate, most available catalytic sites cycle through occupied states. Adding more substrate produces a smaller and smaller increase in rate.
That creates the plateau.
The curve approaches a maximum. The Michaelis-Menten equation writes the relationship as velocity equals Vmax times substrate concentration divided by Km plus substrate concentration.
So saturation is not the enzyme getting tired. It means substrate is no longer the main limiting variable for the available enzyme population.
The enzyme continues to turn over. The rate is limited by how much active enzyme is present and how quickly each active site completes its catalytic cycle. Vmax is the maximum velocity approached at saturating substrate for a fixed amount of enzyme. In the classical model, Vmax equals Kcat times total enzyme concentration. Kcat is the turnover number, the number of catalytic cycles one active site can complete per unit time at saturation.
Then, losing active enzyme or reducing catalytic turnover tends to lower Vmax.
Km is different. The Michaelis constant is the substrate concentration that produces 1/2 of Vmax under the model.
Then, a lower Km means less substrate is required to reach half maximal velocity. What does it mean if the measured curve shifts to a higher Km?
It means more substrate is required to reach half maximal velocity. Before calling that lower affinity, define the word. Affinity describes how tightly 2 binding partners, such as succinate and an empty SDHA site, bind one another. A direct equilibrium binding experiment can describe that relationship with a dissociation constant, or Kd. A lower Kd means tighter binding.
Then, why do enzyme questions often call a higher Km lower affinity?
Because the rate curve behaves as though more substrate is needed, the precise phrase is lower apparent affinity. Here, apparent means what this kinetic experiment seems to show under these conditions, not necessarily a permanent property of the enzyme-substrate pair.
So Km comes from reaction velocity, whereas Kd comes from binding equilibrium. They are not automatically the same number.
In some simple mechanisms, Km tracks substrate binding closely. In others, catalytic steps also contribute. A change in apparent Km does not by itself prove that the intrinsic binding strength of succinate at an unoccupied SDHA site changed.
That gives names to the opening contradiction: a low substrate rate gap and a shared high substrate plateau.
The plateau will tell us about Vmax. The substrate position of the curve will tell us about apparent Km. We still need the full table before deciding what malate did.
One thing bothers me. If the curve only approaches Vmax, no finite substrate concentration literally reaches the mathematical plateau, right?
Real Michaelis-Menten curves approach Vmax. When a teaching table repeats the same high substrate rate, read it as a rounded or simplified plateau. The inhibition table is easier to remember when you derive it from binding states. Keep the model attached to SDH. Free enzyme means the succinate binding region on SDHA is empty. ES means succinate is occupying that region. In classical competitive inhibition, the inhibitor binds free enzyme in a way that excludes substrate binding. The enzyme cannot occupy the inhibitor-bound state and the succinate-bound state at the same time.
More substrate gives substrate more chances to capture free enzyme. At sufficiently high substrate, the reaction can still approach the original Vmax.
The result is unchanged, Vmax with a higher apparent Km. Pure non-competitive inhibition is a special mixed pattern. The inhibitor acts equally on free enzyme and the enzyme-substrate complex. It reduces usable catalytic capacity without favoring one binding state over the other.
So, would Vmax fall while Km stays the same, with no rescue by added substrate?
Yes, in uncompetitive inhibition, the inhibitor binds only the enzyme-substrate complex. Both Vmax and Km decrease. Mixed inhibition allows binding to both free enzyme and the enzyme-substrate complex, but with unequal strengths. Vmax falls, and apparent Km can move up or down.
So, mixed inhibition is not one fixed Km change. It depends on which enzyme state the inhibitor favors.
An irreversible inhibitor adds another idea. If it permanently removes active enzyme, the effective enzyme concentration falls, so Vmax commonly falls. A velocity table alone does not prove covalent bonding or irreversibility. You would need evidence such as time-dependent inactivation, failure to recover after washout, or direct detection of a covalent adduct.
Does binding at a different site automatically mean non-competitive inhibition?
Physical location and kinetic class are related, but they are not interchangeable labels. An allosteric site is a site away from the substrate binding region. Binding there can change the enzyme's shape and indirectly prevent substrate binding. Kinetics tells us which binding states and rates fit the data. It does not draw an atomic map of the enzyme. Now we can read the actual prompt. Succinate dehydrogenase is located in the inner mitochondrial membrane and catalyzes the oxidation of succinate to fumarate.
That sentence establishes the enzyme, location, substrate, product, and reaction. It does not yet classify malate.
The experiment then asks whether malate changes SDH activity. Reaction velocity is measured with and without a fixed quantity of malate, as succinate concentration is gradually increased.
The independent variable is succinate concentration. The dependent variable is reaction velocity. The amount of malate is fixed, and the no malate condition is the control.
Good. That setup matters. We are comparing two substrate response series under otherwise matched conditions. One low concentration value cannot define the mechanism. We need the trend across the full substrate range.
At 2 millimolar succinate, the rate is 80 micromoles per liter per second without malate, and 40 with malate. At 8 millimolar, the rates are 200 without malate and 120 with malate. At 16 millimolar, the rates are 280 without malate and 200 with malate. At 64 millimolar, both rates are 400. At 128 millimolar, both rates are again 400.
The low substrate values show inhibition, but one row cannot classify it. Keep all 5 rows in view while you choose.
Which statement about malate is most accurate in this experiment? A. It alters the maximal velocity of the reaction. B. It binds the enzyme at a different site than succinate. C. It covalently binds the enzyme. D. It decreases affinity of the enzyme for succinate. It is a competitive inhibitor of the enzyme. Lock in your answer. At 64 and 128 millimolar succinate, the two conditions converge at approximately 400 micromoles per liter per second.
That shared plateau estimates Vmax. The control Vmax is about 400, and the Vmax with malate is also about 400.
So, malate did not lower the final rate the available enzyme could approach.
Exactly. High succinate also erased the rate difference. Keep both facts. Unchanged Vmax and high substrate rescue.
That already argues against a simple loss of active enzyme. If malate had permanently removed a fraction of the enzyme, the maximum capacity would usually stay lower.
Right. We still have not named the answer. We have established the first kinetic parameter. Half of the estimated Vmax is 200 micromoles per liter per second.
Without malate, the table reaches 200 at 8 millimolar succinate. Km is therefore approximately 8 millimolar.
With malate, 200 occurs at 16 millimolar succinate. The apparent Km is approximately 16 millimolar.
Wait. The apparent Km doubled. The reaction needs about twice as much succinate to reach the same half-maximal rate.
Under the classical competitive model, the ratio of apparent Km to Km is the factor alpha. Here, alpha is approximately 2.
Can we calculate the inhibition constant, Ki, from that?
No. For a simple competitive model, alpha equals 1 plus inhibitor concentration divided by Ki. The problem never gives the malate concentration, so Ki remains unknown.
We now have 3 observations. Unchanged Vmax, increased apparent Km, and rescue by high succinate.
And those observations have to be interpreted together. Unchanged Vmax tells us the original maximum capacity remains reachable. Higher apparent Km tells us more substrate is needed to reach a given fraction of that capacity. Rescue tells us substrate can overcome the inhibitory effect.
That combination matches the classical pattern produced when inhibitor binding and substrate binding are mutually exclusive.
That also closes the hypothesis we opened when malate entered. Its similarity to succinate made mutual exclusion plausible, and the rate pattern supports mutual exclusion at the kinetic level. It still does not tell us the exact atoms or site involved. Notice the reasoning move. We did not identify a familiar molecule and attach a label. We read capacity first, the half-max position second, and rescue behavior third. The most accurate answer is E. In this experiment, malate produces a competitive inhibition pattern.
The three observations now have one kinetic name.
Choice A contradicts the plateau. The maximal velocity stays near 400 in both conditions. Choice C adds a mechanism the experiment never measured. There is no covalent labeling result, washout test, or time-dependent inactivation. The preserved Vmax and substrate rescue also do not fit a simple model in which active enzyme has been permanently removed.
Choice B says malate binds at a different site. Why can we not infer that from competitive kinetics?
Because a rate table does not locate atoms. Competitive kinetics requires mutually exclusive substrate and inhibitor binding. They often compete within the same active site region, but an allosteric change could also make the two states mutually exclusive. This experiment cannot choose a precise physical site. That is what eliminates B. E describes a kinetic pattern the experiment measured. B asserts a physical location the experiment never examined.
D still feels almost correct. The apparent Km did increase.
It is the strongest near miss. If affinity means apparent affinity, the reaction behaves as though it needs more succinate. But D does not say apparent affinity. Read literally, it suggests that succinate's intrinsic binding affinity for an available active site changed, which this table does not establish. D also names only one effect. E names the full kinetic class supported by unchanged Vmax, higher apparent Km, and high substrate rescue. That makes E the more accurate choice. There is an item writing boundary here. If D said lower apparent affinity, both D and E would be defensible, and this would be a weaker question. As written, D leaves out the qualifier that makes the claim precise.
Are we done once we say competitive inhibition?
We are done with the question, but not with the boundary. The data support a classical competitive inhibition pattern under the supplied conditions. They do not show that real mitochondria use only one malate-dependent inhibitory mechanism.
That last boundary returns us to eno oxaloacetate.
SDH can oxidize malate to enol oxaloacetate, which can inhibit the enzyme. That real biochemistry does not erase the pattern in the supplied table. It tells us not to turn a kinetic label into a complete structural story. Change one variable and watch the answer move. If the inhibitor lowers Vmax but leaves Km unchanged, and high substrate cannot restore the plateau, the classical answer becomes pure non-competitive inhibition.
If both Vmax and Km decrease, think uncompetitive inhibition.
If Vmax decreases and Km moves either up or down, think mixed inhibition.
If Vmax stays the same, apparent Km rises, and high substrate restores the rate. Think competitive inhibition.
Correct. If a future question shows progressively stronger inhibition with pre-incubation, failure to recover after washout, or a detected covalent adduct, then irreversible or covalent inhibition becomes supportable.
The table does not need to be memorized as 4 isolated rows. Each row follows from which enzyme state the inhibitor can bind and whether active capacity remains available. What if the next exam replaces the table with a Lineweaver-Burk plot?
The biology is unchanged. A Lineweaver-Burk plot graphs 1 over velocity against 1 over substrate concentration. Taking the reciprocals turns the saturation curves into straight lines. The y-intercept is 1 over Vmax, and the x-intercept is -1 over Km.
For competitive inhibition, Vmax stays the same. So the two straight lines share the same y-intercept.
Right. Apparent Km rises, the slope becomes steeper and the x-intercept moves towards 0. Do not memorize that picture separately. It is the reciprocal form of the same Vmax and Km changes.
We have solved an isolated enzyme experiment. Where does the same SDH machine matter in disease?
The nuclear genes SDHa, SDHb, SDHc, and SDHd encode the 4 subunits we assembled earlier. Pathogenic variants in these SDHx genes can underlie hereditary, paraganglioma, pheochromocytoma syndromes.
What are those tumors?
A paraganglioma is a neuroendocrine tumor arising in extra-adrenal paraganglionic tissue. A pheochromocytoma is a paraganglioma in the adrenal medulla. Their relationship to SDH begins with the same reaction we started with. When SDH function is lost, succinate oxidation slows, and succinate can accumulate. Succinate then inhibits some 2-oxoglutarate-dependent dioxygenases. These are enzymes that normally use oxygen and 2-oxoglutarate, also called alpha-ketoglutarate, to modify other molecules.
How does that create a false hypoxia signal?
HIF prolyl hydroxylases are one group of those dioxygenases. Hypoxia-inducible factor, or HIF, is a transcription factor that turns on a cellular hypoxia response program. Its oxygen-regulated alpha subunit is called HIF-alpha. When oxygen is available, the hydroxylases mark HIF-alpha by adding hydroxyl groups. The von Hippel-Lindau, or VHL, tumor suppressor complex recognizes hydroxylated HIF-alpha and directs it toward degradation.
If excess succinate inhibits the hydroxylases, HIF-alpha can persist even while oxygen is available.
Correct. The cell activates part of a hypoxia response despite adequate oxygen. That state is called pseudo-hypoxia. Succinate can also inhibit DNA and histone demethalases, enzymes that normally remove methyl marks. Their inhibition can contribute to abnormal hypermethylation.
So the same reaction gives us a second causal chain. SDH loss, succinate accumulation, dioxygenase inhibition, altered HIF and epigenetic regulation, then tumor predisposition.
With one boundary, That is an exam-level mechanism summary, not a claim that HIF alone explains every feature of SDHx-associated tumor biology.
We started with one physical SDH complex, used its binding states to explain the curve, and then let the table determine the answer.
Use the same order on the next enzyme question. Read the high-substrate plateau to assess Vmax. Find the substrate concentration at half Vmax to estimate Km. Then ask whether high substrate rescues the rate.
For this table, same Vmax, higher apparent Km, and high substrate rescue.
That is a competitive inhibition pattern. Answer E.